Hi, my name is Evan Woodruff, and my topic was circular motion. Many people think that um, when a particle is traveling in a circular motion, there is zero acceleration because it is going the same speed all the way around. But in fact, there is an acceleration. The definition of acceleration is change in velocity, and velocity has two components. One is its magnitude, and the other is its direction. And so, although it's not changing magnitude, it is changing direction. The velocity vector is always perpendicular to the radius, but tangent to the outside edge. And the acceleration vector is always perpendicular to the outside edge, pointing inwards towards the center of the circle. The reason it's always perpendicular to the outside edge is because the speed is not changing. Only the direction of the velocity is changing. So if the acceleration vector, let's say, was maybe over here instead of straight perpendicular, there some of the component would change actually the magnitude of the velocity vector, but since it's at a constant velocity, actually a constant speed, it's always pointing towards the center. I chose problem 38 from the book. It reads, an athlete swings a ball connected to the end of a chain in a horizontal circle. The athlete is able to rotate the ball at the rate of 8 revolutions per second when the length of the chain is 0.6 meters. When he increases the length to 0.9 meters, he is able to rotate the ball only 6 revolutions per second. A. Which rate of rotation gives the greater speed of the ball? B. What is the centrifugal acceleration of the ball at 8 revolutions per second? And C. What is the centrifugal acceleration at 6 revolutions per second? This is my drawing for the problem 38. There is a ball connected to a chain swinging in a circular motion. Part A asks us to find which rate of rotation gives us the greatest speed. And so I calculated speed as distance over time, which equals 2 pi r, which is the circumference of the circle, which is distance, over seconds, times the number of rotations. So when the chain is 0.6 meters and the ball travels 8 revolutions per second, we calculate that out and we get 9.6 pi meters per second. And then when we calculate it for when the chain is 0.9 meters and the ball is 6 revolutions per second, it calculates it to be 10.8 pi meters per second. So when the chain is 0.9 meters and the ball is revolving 6 times per second, there is a greater speed. For part B, we were asked to find the centrifugal acceleration for when it is 8 revolutions per second with a chain of 0.6 meters, and to find acceleration we square the velocity and divide it by r, which is the radius, and when we do that we get 1,516 meters per second squared. And in C we were asked to find the centrifugal acceleration of when it was 6 revolutions per second while the chain is 0.9 meters long. And when you calculate that out as well, we get 1,279 meters per second squared. And that was my presentation on circular motion. Hope you enjoyed it, and have a nice day.